All right, people, welcome back. So now that we have met surface integrals, I think one of the takeaways from our talk about surface integrals is that it's quite a bit of work to um, just compute even just one surface integral. So hopefully by the end of this course, we're going to get maybe some easier, maybe sort of shortcuts that will allow us to maybe trade a surface integral for a nicer integral. Kind of like how the fundamental theorem of line integrals and Green's theorem, they allow us to trade a line integral for something that might be easier to handle. So we will get something like that for surface integrals. But before we get there, we have to meet two new concepts related to vector fields, and these are called divergence and curl. So let's start with a vector field on three-dimensional space. So we'll have its three component functions are p, q, and big R. Okay. Then the divergence of this vector field is a scalar valued function associated to the vector field. So it's written like this, div f, and it's called the divergence of f. It's a scalar valued function whose value at every point of space is given by the value of the partial derivative of the first component p with respect to the first variable x, plus the partial derivative of the second component q with respect to the second variable y, plus the partial derivative of the last component, big R, with respect to the last variable, z. Okay. And so we could also define this for a two-dimensional vector field. So we just have the last component just wouldn't be included there because there wouldn't be one. Okay. And in fact, divergence is something you can define for a vector field on any dimension of space. So in this course, we're mostly concerned with dimensions 2 or 3. That's fine. Okay, so what is this divergence thing? Well, what it tells us is sort of the extent to which a vector field is flowing out from each point of its domain. So recall our sort of most favorite example here of the vector field that swirls kind of in circles around the origin. And if you recall the picture that we had drawn of this in GeoGebra, I think it was a little bit more clear when everything is filled in, that sort of at each point, everything that's kind of flowing out is also kind of flowing back in a sort of equal way. So that this vector field has divergence equal to 0 at every point of the plane. And when that's the case, when you have a vector field big F whose divergence is 0 everywhere, we say that F is incompressible. Just a little bit of jargon for you there. Okay, on the other hand, let's look at this other vector field. Big F is x in the first component and y in the second. You might recognize that's like the gradient, right, of the function little f of xy equals to 1/2 x squared plus 1/2 y squared. But notice this one's divergence is 1 plus 1, which is 2. Okay. And notice here, kind of just looking at maybe the origin or something, it looks like everything is flowing outward from the origin there. Okay, so we have positive divergence. If things were turned around and flowing inwards, we'd have negative divergence. Okay, so there's a slightly easier way to sort of write the computation for divergence using this thing called the vector gradient operator. And so just in general, whenever you hear this buzzword operator, it's typically used in mathematics, at least, in the context of being a function whose domain is itself a collection of functions. So maybe the inputs are functions of one type and the outputs are functions of maybe a possibly different type. So basically think of it as a gadget that does stuff to functions and turns them into other functions or maybe other mathematical objects, other mathematical gadgets. So for example, in Calculus 1, we met the derivative, right? We call maybe d by dx. And this is an operator that takes a scalar valued function of one variable, say f of x, to its derivative, df dx, otherwise known as f prime of x. So that's one. Our partial derivative operators are also operators on functions. they're operators on functions of more than one variable. And the gradient itself, when you put all those guys together, the gradient is an operator whose inputs are scalar valued functions, but whose outputs are vector fields, right? And we can think of vector fields as a certain type of function, but we might just like to think of them as just vector fields. That's fine. So really, we can write this gradient without a sort of function attached to it. We can just write it as a vector whose components are operators themselves. The first component operator is the partial derivative with respect to x. The second is the partial derivative with respect to y. And the third is the partial derivative with respect to z. And then you can think of this as then kind of satisfying what you think, that when you apply this operator to a scalar valued function, little f, it just applies the respective operators in each component to f and gives you what we think of as the gradient of the function little f. Okay, so with this vector operator notation in place, we get a kind of nice way to write the divergence of a vector field big F. So if big F has component functions p, q, and r, then we can write the divergence of big F is really the dot product of this vector valued operator with our vector field big F, right? It's the partial derivative of p with respect to x plus the partial derivative of q with respect to y plus the partial derivative of r with respect to z. So that's kind of nice looking. And okay, that's going to come back and be useful in what we're going to talk about next. So next up is the curl of a vector field. And so this one is really only defined for vector fields on three-dimensional space. So we'll let f be a vector field on three-dimensional space. And its three component functions are p, q, and r. Okay. And now the curl of a vector field is going to be a new vector field. So this is a little bit different than divergence. Divergence gave us a scalar valued function. Curl is going to give us yet another vector field. And the three component functions of that vector field are going to be given by these differences of partial derivatives here. We have the partial derivative of r with respect to y minus the partial derivative of q with respect to z in our first component. In the second component of curl of f, we have the partial derivative of p with respect to z minus the partial derivative of r with respect to x. And in the last component of the curl, we get the function that is the partial derivative of q with respect to x minus the partial derivative of p with respect to y. Okay. So this might be kind of hard to sort of commit to memory, so there might be an easier way to think of writing it, as it's really, if we take that gradient vector operator, we can write curl of f as the cross product of that gradient vector operator with our vector field f, okay? And since cross product only makes sense for vectors in three-dimensional space, curl of f is only really going to make sense when we have a vector field on three-dimensional space. Okay, and one more interesting thing to notice here is that you might recognize at least one of these. Oh, right. This component here. This looks exactly like the integrand from the double integral side of Green's theorem, right? So that is no coincidence, and we will see a little bit later about how that will come and sort of generalize Green's theorem in the later part of this talk. We'll see that. Okay, so the meaning of curl, though, we get a new vector field associated to this old one, big F. Well, what does curl of F mean? It's at every point you get a vector that is related to the original vector field F in the sense that it is some kind of axis of rotation around which the original vector field is sort of moving. So as a sort of our favorite example, again, if we take that vector field that swirls around the origin in the xy plane in sort of circles, let's make that a three-dimensional vector field by just setting the third component to always be 0, so that we have that same behavior in the xy plane for all the xy planes at every single height z, right? So then it looks like the sort of z-axis is a sort of axis around which this vector field is sort of flowing, right? And if we compute the curl, we'll cover up the first components here, and we'll say, okay, this partial derivative is 0 minus that partial derivative is also 0. So the first component of curl is 0. Okay, for the second one, we'll cover up this guy in the middle here, and we'll say, okay, let's do the partial derivative of minus y with respect to z minus the partial derivative of 0 with respect to x. That gives us 0 again. And if we cover up the last components, you get the last one here. We get the partial derivative of x with respect to x, that is 1, minus the partial derivative of minus y with respect to y, that is minus 1. So we'll get 1 minus minus 1, which is 2. Oh, okay. So now we can compute here that then curl of f is the constant vector field that is always pointing 2 units in the positive z direction. So that direction there is then telling us that that z direction is the sort of axis of rotation around which this vector field is flowing. And the length of this vector tells us something about the rate at which that rotational flow is occurring. All right. So then let's talk about when is the curl of a vector field equal to 0 at every point. So let's see. When that happens, we say that the vector field f is irrotational, just a little bit of jargon. And so one nice particular instance is when we have a conservative vector field. Remember, this is a vector field that is the gradient of some scalar valued function little f. So its components are partial derivatives of little f with respect to x, y, and z. So let's compute the curl of one of these guys. If we compute the curl, we get, for the first component, we'll get the second partial derivative of f first with respect to z and then with respect to y, minus the second partial derivative of f first with respect to y and then with respect to z. Okay, for the second component, we'll cover up the second components here, and we'll get that we have the second partial derivative of f first with respect to x and then with respect to z, minus the second partial derivative of f first with respect to z and then with respect to x. Okay, and then in the last component, not surprising at this point then, if we cover up the last components here to compute the cross product, we'll get that we have the second partial derivative of f first with respect to y and then with respect to x, minus the second partial derivative of f first with respect to x and then with respect to y. Now you guys might recognize these as the corresponding sort of mixed partial derivatives, right? Mixed second partial derivatives here. And so all the functions that we've studied thus far have been well enough behaved that these sort of respective pairs are always equal to each other, right? In particular, if these second partial derivatives are continuous, then we get to invoke the Clay-Rose theorem, which I like to call equality of mixed partials, which then says that each one of these components for curl of f is going to be 0. So if you have a nice enough conservative vector field where the function at hand, little f, has continuous second partials, then curl of any one of those vector fields is going to be everywhere 0. Okay, so here's some more consequences, I guess. So if, let's suppose we start with a vector field big F whose component functions are p, q, and r. And let's say that those p, q, and r have continuous partial derivatives. So what we've just shown on the previous slide then is that if the curl of our vector field big F is not 0, then big F could not be conservative. All right, so that's kind of a nice way that we have now for vector fields on R3 to show that they are not conservative, if they're not conservative. Okay, so let's suppose now that we've taken curl of f, and we get this expression here as was our definition. Now let's compute the divergence of this guy. So if you start with a vector field big F, you can apply the operator curl and get a new vector field curl of f. And then you can apply the vector field div, as they call it, and get a scalar valued function, the divergence of the curl of f. And what happens there? Well, we'll take the partial derivatives of this expression with respect to x, plus the partial derivative of this second expression with respect to y, plus the partial derivative of this third expression with respect to z. And what that gives us then is, again, a bunch of second partial derivatives that are all sort of mixed partial derivatives down here. And it looks like they go together in pairs, right? So if we have the second partial derivative first with respect to y, then with respect to x, we have over here minus the second partial derivative of r first with respect to x, then with respect to y, right? And they all kind of go together in these opposite pairs like that. And so if p, q, and r all have continuous partial derivatives, well, actually, they have to have continuous second partial derivatives. I guess I probably should have had up here. Then we can say that these two guys are equal, or sorry, these two guys are equal to each other. These two guys are equal to each other, and these last two are equal to each other as well. And so then subtracting one from the other gives you 0 plus 0 plus 0, which is, 0. So divergence of curl of f in at least the nice cases where f has its component functions having enough nice continuous partial derivatives, it will follow then that if you do curl followed by divergence, you get the scalar valued constant function equal to 0. All right. So now that we've met curl and divergence, we can sort of go on and get some new good theorems that will help us trade out a surface integral for maybe an integral that is more friendly to deal with. So stick around for that.